Welcome back to the GD&T Master Course. I'm thrilled we're jumping into Lesson 6 today because we're finally tackling the very heart of the entire system, the feature control frame. This is the standardized language that mechanical designers, manufacturing engineers, and quality inspectors all over the world use to communicate exactly how a part should be built and measured.
So, here is our game plan for this explainer. We're going to break down the foundation of these control frames, look at the symbols and tolerance zones, figure out datums and material modifiers, practice reading some real-world callouts, and then cap it off by showing you how to avoid common mistakes, plus some really cool inspection takeaways. All right, Section 1, Foundation of Control Frames and Decoding the Chaos. Let's get right into it. If you look at a standard engineering drawing, man, it can look totally chaotic, right? Lines, numbers, and symbols are just flying everywhere. But don't let it intimidate you. Every single one of those geometric requirements, every boundary, and every constraint is actually communicated through a super simple, highly standardized structure. You don't need a whole paragraph of notes to explain how round a hole needs to be because we have a dedicated tool for that. And that tool is the Feature Control Frame, or FCF for short. Think of the FCF as the absolute Rosetta Stone of manufacturing. It takes your theoretical, perfect design in your CAD software and translates it into a measurable, physical reality on the shop floor. It bundles every single rule for a specific feature into one neat little rectangular box. Now, you literally read a feature control frame just like a sentence, reading straight from left to right. First up, you've got the geometric characteristic symbol. That's basically your verb, telling you what kind of control is happening. Then you hit the tolerance value in its shape, your adjective describing how big the tolerance zone actually is. And finally, on the right side, the datum references. That's the context, telling you exactly what you are measuring this feature against. Moving on to Section 2, Symbols and Tolerance Zones, the verbs and adjectives. So according to the updated ASME 2018 standards, we divide these geometric controls, our verbs, into 5 major categories. We've got form controls, which dictate the shape of a feature all on their own, no datums needed. We have profile controls for those complex 2D curves and 3D surfaces. Orientation controls handle your angles, so things like perpendicularity and parallelism. Location controls, primarily true position, manage exactly where a feature lives in space. And finally, runout controls, which manage the variation, or basically the wobble, of a surface as you rotate the part 360 degrees. But here is the absolutely crucial takeaway. When we use one of these symbols, we aren't just slapping a plus or minus onto a flat dimension. No way. These symbols create a literal and visible 3D envelope in space, whether that's a cylinder, parallel planes, or profile boundaries offset from a true curve. The physical part you actually manufacture has to fit entirely inside that specific 3D envelope. Next up, Section 3, Datums and Material Modifiers, Establishing Context. Let's look at the compartments on the right side of the frame. Datums are, well, they're everything. They aren't just imaginary points floating in space. They establish the physical hierarchy of how a part actually sits in a gauge or an assembly. Think about it. Any part in space has 6 degrees of freedom. It can move along 3 axes and rotate around 3 axes. We read datums strictly from left to right: primary, secondary, and tertiary. Your primary datum is your very first physical point of contact, like slapping a part flat down on a table. The secondary datum stops it from sliding around, and the tertiary datum locks it in completely, so you can measure it perfectly every single time. Now, tucked right next to your tolerance values or datums, you might spot a little circled M or L. These are your material condition modifiers. We'll do a deep dive on these in a later lesson, but for now, just know they define how a feature's size interacts with its geometric tolerance. MMC, or maximum material condition, actually gives you bonus geometric tolerance as a hole gets bigger, which is a total game changer for clearance fits. LMC, least material condition, is used to protect things like minimum wall thickness from breaking. And if you don't see any symbol at all, that defaults to RFS, meaning the geometric tolerance applies regardless of feature size. All right, Section 4, Reading Real-World Callouts. Let's put this all together and practice translating this language on a mounting bracket. Imagine we're looking at a through hole on this bracket. Reading left to right, we see the crosshairs. So we literally say, the feature's center axis must be positioned within a 0.25 diameter cylindrical tolerance zone. We see that circled M, so we add at maximum material condition. And finally, the context, relative to primary datum A, secondary datum B, and tertiary datum C. See, it's literally just reading a highly specific technical sentence to guarantee that bolt will fit. Let's try another one. Maybe we're looking at the flat meeting face of that exact same bracket. We see the upside-down T, that's perpendicularity. So the callout reads, the feature must be perpendicular within a 0.10 tolerance zone. Notice there's no diameter symbol here, so we know this zone is usually just between two parallel planes. And then relative to primary datum A. Basically, this bracket face has to stand straight up at 90 degrees to datum A, completely trapped within that tiny 0.10 gap. And one more. Let's look at a profile control for the curved outer edge of our bracket. That half circle symbol dictates the entire surface must fall within a 0.50 tolerance zone relative to datum A and datum B. Profile is incredibly powerful, you guys, because it actually controls the size and the form of that complex bracket surface simultaneously. Moving on to Section 5, Avoiding Common GD&T Mistakes. Because when this language gets misinterpreted, perfectly good parts get scrapped or failing parts get shipped. A massive disaster we see on the shop floor all the time is reading datums out of order. If you fix your part on datum C first instead of datum A, well, you've completely ruined the measurement coordinates and the inspection logic. Another huge trap is confusing the tolerance value inside the box with the actual dimension of the feature itself. Remember, the feature control frame tells you the size of the boundary your deviation must stay inside, not the size of the physical part itself.
Oh, and here's a big one. Please do not use the concentricity or symmetry symbols. These were notoriously confusing and an absolute nightmare to measure reliably because they required inspectors to find theoretical derived median points in space. Actually, they were so bad that the ASME 2018 standard officially banned them. Today, you just use position or profile controls instead. They're much easier to verify and serve the exact same design intent.
Finally, Section 6, Inspection and Key Takeaways. Let's talk about how we actually validate all of this on the shop floor. So, how do we prove a part actually meets the sentence we just read? Quality engineers calculate what's known as the virtual condition. This is basically your worst-case envelope boundary. Ask yourself, if a hole is machined to its absolute smallest allowed size, and it is also tilted to the absolute maximum edge of its positional tolerance, will the mating pins still fit through it? Inspectors use this exact logic to design physical go and no-go gauges to guarantee the part actually works in the real world. And on the digital side, things are even cooler. Modern manufacturing relies heavily on CMMs, or coordinate measuring machines. When a designer uses semantic GD&T, meaning the feature control frames are built with actual data intelligence right inside the 3D CAD model, the CMM software can import those rules directly. The software literally guides the operator to align the datums, completely eliminates manual math errors, and spits out an automated pass-fail report based exactly on what that feature control frame dictated. It's incredibly fast and insanely accurate. I want to leave you with this direct quote from the ASME standard. The as-designed dimension value does not establish a functional or manufacturing target. Let that sink in. Your base dimensions in CAD are really just theoretical. The feature control frame is the ultimate authority on what makes an acceptable, functional part. Without it, you are literally just guessing. That wraps up this explainer. You now have the foundational key to reading any GD&T drawing. But the next time you hold a physical part, ask yourself, are you actually measuring the object itself? Or are you measuring the invisible mathematical envelope that guarantees it'll work? Think about it. Next lesson, straightness, the first form control.